Linearly varying dielectric constant. Two conducting plates with area A are separated by distance d. Between the plates is a material with a dielectric constant that varies linearly from a value of unity next to one plate to kappa next to the other plate. Part A. What is the capacitance of this device? We can envision this as a continuum of capacitors with differential plate separation connected in series. The reciprocal of the capacitance of a differential slice is then dx over kappa of x epsilon 0a, where kappa of x is the dielectric constant specific to that locale. And part B showed that this result matches the expected result when kappa becomes 1. Okay, so we have these two parallel plates, area A, the separation between them is d. We have a linearly varying dielectric in between them, and this is my x-axis here, going from the bottom plate to the top plate, and kappa of x is equal to ax plus b. It's a linearly varying function of x. When x is equal to 0, we are at the bottom plate. Kappa at x is equal to 0 is equal to 1. So if I substitute x is equal to 0 here and say that this should be 1, this implies that b must be equal to 1. When x is equal to d, that means I have reached the top plate. The value of kappa at x is equal to d is a times d plus 1, and that is equal to kappa. Therefore, I find that a must be equal to kappa minus 1 over d. So with that, I find the dielectric constant kappa as a function of x to be kappa minus 1 over d x plus 1, or I can rewrite this as kappa minus 1x plus d over d. And I can think about this as a continuum series of capacitors connected in series. And why is that? Because going from one plate to the other plate, I'm looking at the voltage between the plates of this differential capacitor here. And for all of those, the voltages add up to the total voltage between the top and bottom plate. So since the voltages add up, they will have a series connection. If the voltages were the same, then it would be a parallel connection. Okay, so what is the capacitance at position x? It is the value of the dielectric at that position, epsilon 0a, the area, divided by the distance between the plates, which is the differential distance, dx, differential distance. And what is the 1 over the capacitance? 1 over c of x, the reciprocal, is dx divided by kappa of x epsilon 0 a. Now I try to find the equivalent capacitance of this configuration. Because these are capacitors connected in series, 1 over c equivalent is equal to integral x goes from 0 to d 1 over c of x. So I'm adding up all of these capacitances. And this is equal to, so 1 over c of x was given here. So I'm going to substitute for 1 over c of x, kappa of x over epsilon 0a. This will be d over epsilon 0a, because here is kappa of x substituted here. That gives me, because it's the reciprocal of kappa, it's going to give me d over kappa minus 1 x plus d. So this will become d over epsilon 0a integral from 0 to d. I have dx divided by kappa minus 1 x plus d. So this part, d over kappa minus 1 x plus d, is just 1 over kappa. It's the reciprocal of the dielectric constant. And in order to perform this integral, I'm going to let u is equal to kappa minus 1 x plus d, transformation of variables, so that du will become kappa minus 1 dx. And let's take it from here. So this will give me 1 over c equivalent is, for dx, I will substitute du over kappa minus 1. So this will become d over kappa minus 1 epsilon 0a integrated from x equals 0, u is equal to d. When x is equal to d, it's going to be kappa d minus d plus d, so it's going to be kappa d. So u minimum is d, u maximum is kappa d, du over u. And this will give me 1 over c equivalent is d over kappa minus 1 epsilon 0a. Now I will obtain natural logarithm of u evaluated between kappa d over kappa d and d, natural logarithm of kappa d minus natural logarithm of d, and that will give me just natural logarithm of kappa. So I'm ready to write my final answer for the equivalent capacitance. It is, now I take the reciprocal, so I will have kappa minus 1 epsilon 0 divided by natural logarithm of kappa a over d. This is natural logarithm of kappa, so d natural logarithm of kappa is at the bottom, and kappa minus 1 epsilon 0a is at the top. So that's the equivalent capacitance. Now let me check the limit when kappa goes to 1. So in the limit kappa goes to 1, I have kappa minus 1 divided by natural logarithm of kappa, which is 0 divided by 0. So in order to find this limit, I'm going to use L'Hopital's rule. So in the limit kappa goes to 1, the derivative of the top with respect to kappa is equal to 1. The derivative of the bottom is 1 over kappa. So that's going to become limit as kappa goes to 1, kappa which is 1. So here I've used L'Hopital's rule. So I take the derivative of the top and divide it by the derivative of the bottom in order to get rid of this 0 over 0 uncertainty. So what happens to the equivalent capacitance then as kappa goes to 1? As kappa goes to 1, kappa minus 1 over natural logarithm of kappa is replaced with 1, I obtain epsilon 0 A over D. That's the limiting value of the equivalent capacitance. And what is this? This is a parallel plate capacitor. Parallel plate capacitor. No dielectric. It's just air capacitor. Okay, so in this problem we had a linearly varying dielectric constant between the bottom and top plates of a capacitor, and such that the dielectric constant is 1 at the bottom plate and it's kappa at the top plate, which gives us kappa is a function of x, kappa minus 1x plus d over d, where d is the separation between the bottom and top plates. And this is equivalent to having a series of capacitors connected in series, because the voltages add up to the voltage difference between top and bottom plate. That means 1 over C of C equivalent is the integral from 0 to d 1 over C of x. And the capacitance at position x is kappa of x epsilon 0 A over dx, where dx is the differential separation between the plates, intermediate top and bottom plates. And that gives me this integral, and I can easily evaluate this integral by doing this transformation of variables, and I find that it is 1 over C equivalent is d over kappa minus 1 epsilon 0 A natural logarithm of kappa. And if I look at the limit kappa goes to 1, I see that the equivalent capacitance becomes epsilon 0 A over D, which is the parallel plate capacitor without a dielectric. So there is no dielectric here. Kappa is equal to 1 everywhere, and it is just this air, parallel plate capacitor filled with air.